So the lecture notes that I'm going to be using are the PowerPoints that you can find online. So like I said, you can download those PowerPoints, print out, you know, the nice 6 slides to a page or something like that if you want to follow along that way. Or you don't even have to print it out because you can look at it later on, and I'll also have my own notes, annotated notes with some added slides maybe here and there. I'll make that available online as well. So let's take a look at what's up. So chapter 1, like most chapters in textbooks and stuff like that, are a bunch of definitions. Not moving. All right, let's try that again. Okay, I think it's working now. So most of the definitions for what I care about are going to be in the first 2 sections here. The 3rd and 4th sections really talk about how statistics is more applied in terms of you know, designing experiments or running not exams, but tests to test hypotheses and things like that. So I personally think in terms of a statistics course that's really important, but in this particular course we're a little bit more focused on the math side of things, and usually the critical thinking design of experiments part would be covered in like a statistics offered in the social science course or something like that. We do have some questions related to these things in the homework assignments. They're kind of like thinking problems. So we'll take a quick look at them, but I won't stress them too much in this class. I do like definitions though, so I will stress a definition. So some of these things I'll just breeze through and maybe not even read, like this one. But when it comes to things that I feel are important, I think I'll stay and talk a little bit about some of these things. So first definition that we're going to have here, actually the first definition should have been statistics, but the first definition that they give here in this PowerPoint presentation is the data. So data, it's kind of hard to describe it, and I don't know if this definition does justice to this, but we'll make do. In this particular case, they say that data is an observation that has been collected, or a set of observations that have been collected. So some examples would be measurements of something, or a gender or survey response, yes or no, or something like that. So measurements such as height or age or number of keys in your pocket, miscellaneous things like that. So anything that you would collect basically would be considered a data or data point. And data as a whole is the collection of observations or things that you've collected. The next definition is a little tricky. Statistics has 2 definitions that we'll see in this chapter. But the first definition of statistics describes statistics as a subject. And statistics as a subject is a collection of methods for planning studies and experiments. That's kind of like the first step of statistics. Next is to obtain data, collect data, and then organizing, summarizing, presenting, analyzing, interpreting, and then drawing conclusions. So this will be the first question on your midterm. Define statistics. So you can use it this definition word for word, or you can see if you can find a way to translate it. But it's a science of creating an experiment, collecting data, analyzing it, and drawing conclusions. I like to think of this as statistics with a capital S. And I say that because statistics will be defined again as something else later on. So you have to find a way to make a distinction between the two definitions of statistics. Okay. Next slide, population. So when we say population in this class, and you guys will be drilled if you go to Frank's sections a lot, you'll be drilled with the idea of a population and this other thing called a sample. So a population is a complete collection of all elements that you're studying. So I might be interested in studying all the students or maybe all the statistics students in Cañada College. So that could be my population, or all the students in Cañada College. So the idea behind that is that you have a group of things that you're studying, and then there's a good chance that that whole group that you're studying is something that you won't be able to collect. You won't be able to collect off of the whole group. Maybe you can, but maybe the chances are if you're doing statistics, chances are you're not going to be able to collect all of them. So instead of being able to collect the whole population, you would collect a sample. So I want to go talk about sample first. A sample is a sub-collection of a population. So because the population is generally so big, like all the students at Cañada College, you're not going to be able to collect all the data from every single student. You would just get a sample, and the sample would be a sub-collection of that. For example, you, as a class, this class is a sample of all the students taking statistics at Cañada College for the summer. So backtracking to the first definition, if you're able to collect information out of the whole population, then that would be called a census. Now, I say that it's nearly impossible to be able to do this. In fact, when the United States government says that they are collecting information from every single person, and then they report back and say they've collected from every single person, they really haven't collected from every single person. But they still call it a census because that's as close as they can get. When people knock on your doors and say, I need some information about you, and they collect information about you, about your income, about your race, and a bunch of other things. I forget what else is in the census. But a census can occur. I mean, a true census can occur. In our college, and I'm sure in most other colleges, they have what's called a census day, where at a particular day in the semester, this is the cutoff, and this is a collection of every single student. And since you guys are all signed up in Cañada College through WebSmart, we have your information in a data bank somewhere. And so on Census Day, we have a complete collection of everybody. So they have your information, your G number, and a bunch of other things. So it is possible to collect a true census, although in most cases when you're talking about studying statistics, you wouldn't have been able to collect everything. So statistics is usually a study of a sample and trying to generalize that sample to the bigger population. All right. So what is important is that you have a good sample. I'm not going to spend too much time on the slide. But wherever you have sample written down, maybe you can put a little star next to that and say random. It is important that you collect a random sample if you're going to try to generalize information. So if I'm finding out some information about all the statistics students at Cañada College for the summer, I can say that you are my sample, my sub-collection out of the bigger population. Now, is that a good random sample? I don't know if that's such a good random sample because you have actually selected to take a night class and to take a hybrid class. So you might not be a good representation of every single statistics student here in Cañada College for the summer. Turns out that there's like 4 or 5 sections of actual day classes that meet 4 days a week. And so maybe if I collect 2 people from this class and 10 people from the other class and then another 5 people from an online class, maybe that would be a better sample because it would be a little bit more random. It's not just because you guys are here, I'm conveniently collecting your information. That's not a good generalization for all of Cañada College students taking statistics. So the idea that the sample has to be collected in a fair way that's a representative of all the population is important. And that might not always be the case because that might not be possible. All right, types of data. So some of those questions that we were trying to answer, remember the number of beats in the song or something like that, or the temperature. So it's important for us to collect data. So we're going to focus on data. These are the things that we're going to collect. So data, parameter. A parameter is a numerical measurement describing some characteristic of a population. So when you hear the word parameter, you should automatically associate that with population. So a numerical measurement. We haven't studied too many numerical measurements, but can you give me an example of a numerical measurement that would describe a population? Age. So if I want an age would be a specific type of data that I would be collecting. Percentage. Okay, percentage is a little bit closer to what I was going for. But if you were to collect ages out of the whole population, like let's stick with the idea that our population are all the stat students. All the stat students at Cañada College for the summer. That's your population. So I collected a bunch of ages. So let's say my sample was like a sample of 30 ages. So having 30 ages that I've collected wouldn't necessarily be a good numerical measurement. What would be the thing to do with all those 30 ages to find a good representation? Find the average, the mean. So an example of a parameter would be the mean age of everybody in the population. So at census day, I can go to the researcher of the college and say, I want to know the mean age of stat students at Cañada College for the summer. Then she's just going to be able to pull that up and give me a number. And that number would be the mean. And for the mean, the parameter that describes the mean for a population would be denoted by this Greek letter mu. We'll talk about this later, but if you want to practice writing it now, it looks like a U with a little tail. And in Greek, it's more associated with the letter M than U. This is mu. and the M stands for mean. And this is your example of a parameter. This is a parameter. For the parameter, if you're talking about the mean of a population, then I would use mu. Range or standard deviation or things like that. So range, mode. What we have here is basically the same types of measurements that we have for the population. We can also have the same types of measurements for the sample. Okay. So I'll just say this is one example. Let me just give another example. Let's say the standard deviation, because that's another popular one that we're going to be using. And the standard deviation uses the Greek letter S called sigma, and it's written with like an O and a little tail up on top. Now some of you might say, oh wait, shouldn't sigma look like this? And the answer is yes, sigma looks like this. This is capital sigma. This is lowercase sigma. So it is exactly the sum sign in Excel and everywhere else. No, for this case, the standard deviation, we want to use the lowercase sigma, and the uppercase sigma is used as some other symbol. So here are a couple of examples of parameters. This is an M, yeah? So this is one of the things that Frank drills in his sections. Know your letters, know the variables that represent which measurements. Okay, so a parameter is a numerical measurement of a population. Now, we defined statistics earlier, but now here's statistics again. So this is where the word statistics is a little funny because it has two definitions. So when you say a statistic, it means a numerical measurement describing some characteristic of a sample. You know when they say don't be a statistic? This is what they mean. Now, if I collect a smaller sub-collection of all the statistics students at Cañada College in the summer, I would have ages for my collection, my smaller collection. And if I take the mean of that, that might not be the same and probably won't be the same as the mean for the whole population. You know what I mean? So I asked the researcher to give me the mean of all the stat students, then she's going to give me this number, and I'm going to say mu is equal to whatever that number is. And ask for the standard deviation, and I'll say sigma is equal to whatever that number is. Now, if I have a smaller collection, it's not going to hit everybody, all the stat students, so I will have a smaller collection, a sample, and then I would find the mean of that sample and the standard deviation of that sample myself. I won't need my researcher's help because I'm collecting the data myself. So that mean and that standard deviation would be a statistic because it's related to a sample, the sub-collection. Maybe. Well, what we want to do is we have a smaller collection of numbers that I would be studying. So say I didn't have access to my researcher So I just want a good representation, so I would have a smaller sample since I don't know every single stat students in the summer. And so I just have a sample, and then I'll collect information from them, where I'll collect ages and maybe gender or whatever, and I would have that collection of numbers. And all those ages, I would find the average, the mean, but now I can't call it mu because it's not of the whole population. So the symbol that I use for this would be X bar. Because I need to symbolize, I need to represent it with a different symbol from the population parameter. This is a statistic because it's from a subcollection of the population. And my statistic that describes the standard deviation will be represented by S. So there's a difference now in a statistic versus a parameter. A parameter is associated with a population. A statistic is associated with a sample. And these symbols that I'm writing now, we'll use them over and over again, so you'll get to know them a lot. Nope, they just call it standard deviation.
That's what that S over X bar was?
Yeah, earlier when we saw S over X bar, the S stands for the standard deviation. This is X bar. Yeah, I think I'll leave it at that. We'll come back to these symbols again later on in Chapter 2 when we start talking about descriptive statistics. Okay, so all right, so more types of definitions. The type of data that we can collect is that if I want some information about statistics students for the summer, I can find their ages and I can find whether they're male or female, their genders. So those are two different types of data, and this is another way to describe two different types of data. And this is really common when we were talking about research studies and things like that. Quantitative data are collections of things that you would get from a sample that are numerical. So just think of quantity and that should get you thinking about numbers. So something like ages would be an example of quantitative data. Or here their example is weights of supermodels as a quantitative data. Okay? Now, something different from quantitative data is called qualitative. I think categorical might make a little bit more sense, but they use qualitative a lot because it starts with a Q. So qualitative data would be a type of data that's basically non-numeric. If you can't describe it as a number, you would refer to it as a qualitative data. Gender is the simplest example of a qualitative data. Eye color, hair color. What's the last movie you saw? Those are all examples of categorical or qualitative data. Okay? So there's some more breakdowns in these things. Qualitative data, you can't really break that down anymore. We won't be studying this too much. We'll be studying qualitative types of data a little bit later on, but not in great detail. But the first stab of our descriptive statistics is going to be looking at quantitative data. So when we're dealing with quantitative data, there's two levels, two big levels, and then this can be broken down a little bit later on. But quantitative data, numerical data, can be broken into discrete or continuous data. So the next couple of slides will describe each of these things. So discrete. Discrete data, it seems like it's easy to understand, but sometimes they kind of complicate the wordings a little bit. But discrete data, they say here, is either a finite number or a countable number. Now, they use countable in quotes because it's really a mathematical term. Countable means you can count it, 0, 1, 2, 3, and then you can have it go all the way to infinity, but that idea just kind of complicates things. So for our definitions and for our sake, let's just stick with the idea that it's a finite number. And basically, if you can describe it as a whole number, that's usually enough to be able to describe discrete data. Like a good example is the number of eggs that a hen lays. The number of people in a household. The number of students. Usually when they say the number of something, you're counting it. And you're usually counting a finite number, so that's discrete data. No fractions. I don't know. Yeah, maybe not.
Is that why weather is a continuous one?
Weather is continuous because usually you can describe the weather. Usually you say it's 75 degrees, but if you really get technical, you can say 75.4 or something like that. Which brings us to the idea of a continuous. Continuous data is numerical data. They say infinitely many possibilities that correspond to some continuous scale. I don't know if they necessarily need to put the word infinitely many possibilities here. It just scares people, usually. Unless you're a math person, then you would understand what that means. So in math, it turns out that there's the number of numbers between 0 and 1. There's more numbers between 0 and 1 than there are if you were just to count 1, 2, 3, 4, 5, 6. Even if you go to infinity, there's infinitely more numbers between 0 and 1. But that's math. We don't need to do that kind of math. So let's just say if you're allowed to use fractions and decimals, then we're looking at continuous data. So the number of eggs, number of eggs a hen lays cannot be fractional, right? But the amount of milk that a cow produces in gallons is fractional. As you can say 2.5 gallons, you can say 2.34 gallons. So. All right, And just to make things more confusing, we have the discrete and continuous as two. You can separate the quantitative data into these two categories, but now you can break it down even more in a more refined way. And they call them a level of measurement. So there's 4 levels of measurements that they're going to discuss here, and then after this we'll see if we can compare it to what it means in the categorical sense versus the quantitative sense, and what it means in the discrete sense and the continuous sense. So first they talk about nominal level of measurement. So nominal level is basically categories. So if you remember back, that's like quantitative, that's qualitative data. So survey responses, or our example from before, gender, is a nominal level of measurement. So this is something that, another important aspect of nominal level is that you can't put it in a particular order. Like gender, you can't put it in a particular order. You can't say male and female, so you can't say that female goes first. You know. Yeah.
So basically nominal will always be qualitative?
Nominal will always be qualitative. So the next level of measurement, this is like a general level. This is gonna, the level that they're talking about gets refined to the most quantitative. So it starts off at the qualitative end with nominal. Now, nominal you cannot order. The next level down is ordinal level, which you can order. So the big word here, or the big root word, is order, ordinal, something that you can put in a specific order. Now, your course grades, A, B, C, D, or F, is still in the qualitative level, right? It's non-numeric, it's still qualitative, but you can put it in an order that makes sense. The letter grade A is higher than the letter grade B, which is higher than the letter grade C, etc. Versus male and female, you can't say that females are more superior to males, that you would put them first in order, even if you believe that. You can't do that statistically. Like a GPA, for example. Yeah, so 4, 3, 2, 1, 0. So this is also ordinal. That could be placed in order. But saying 4, 3, 2, 1 gives it another level of measurement. So it satisfies the ordinal level, and it may also satisfy another level down, which is the next one we're going to talk about. Yes. What did you say again? It could be both qualitative or quantitative. So this is where the idea of levels of measurements gets a little confusing. It kind of mashes up the quantitative and qualitative. You know, it was nice when we talked about quantitative data and qualitative data, and then we started talking about the quantitative data as being discrete or continuous. So the levels of measurement that we're talking about now kind of mashes those ideas up, and still puts it in some sort of level. And like I said, I'll see if I can get a picture of this thing where it talks about the different levels of things. So ordinal is something that you can place in order. But the differences between values cannot be determined. So there's a D and an F. There's a missing E here. So having those letter grades in ordinal measurements isn't going to make sense, because there's a one letter difference between A, B, C, D, and then there's a 2-letter difference between D and F. So of course, if you assign a number to that, then those distances would make sense. And if those distances make sense, then you're talking about an interval level of measurement. So the interval level of measurement, this is where it really becomes purely numerical, because now you want to take differences between 2 point values. Like between the year 1000 and the year 2000, we know that there's 1,000 years between them. And then if we go from the year 2000 to the year 3000, we know that there's another 1,000 years between them. So basically, if you can put them in a number line where the distances between them kind of make sense as distances, then that would be called interval. And we can even throw -0. So when we're talking about years, we're talking about, we can also go back to BC or BCE, before year 0. So still the difference between 2,000 years, 2000 BC and 1000 BC is still 1,000 years, so that's still the same sort of interval between 1000 and 2000. If you can define a distance between 2 data points, then it's an interval. Now, the way to define interval is that this is an interval level of measurement if there's no natural 0 starting point. Now, if we look at our calendar year, the calendar that we're using, there's a 0 there, right? Whatever that was. But that 0 is kind of arbitrarily chosen. Now, there may be some arguments there, but let's just say, for statistics' sake, that 0 year is arbitrarily chosen. And so it's not what they call a natural starting point 0. So if you can actually find a starting point 0, then you would be at the lowest level of measurement, which is the next one. Lowest or highest? I think it's highest. I don't know. The ratio level of measurement is something that you can put in order, something that has a meaningful distance between them, and something where 0 does indicate as 0, as nothing. Yeah, it shares the same characteristics as ordinal, as interval, but this one has an added feature that 0 means nothing. So the year 0 doesn't mean nothing, right, in our example for interval. But if I'm talking about the amount of coins you have in your pocket, the dollar amount of coins that you have in your pocket, I have no money. I have 0 coins. And that is something that makes sense as a natural 0. So to try to see if I can get a visual of this. That would kind of make sense. Let's see if we can put this in a picture. So let's put the idea of qualitative on top and of quantitative on the bottom. So these lines would be kind of, well, there's a distinct difference between a qualitative and a quantitative type of data. And if we're talking about qualitative data, remember we broke that down even further into discrete and continuous. Now this is where it becomes a little blurred. Well, the nominal isn't blurry. The nominal is clearly non-numeric, so it's categorical. So when we talk about nominal data, then that is clearly going to be qualitative data. Now ordinal is something that you can put in meaningful order, but it doesn't have it doesn't have a meaningful distance between them. So the letter grades would be an example. Now, if you assign numbers to those letter grades as you start looking at GPAs, that changes your data from ordinal to interval now, because so when we start talking about interval, then you have to start talking about quantitative types of data. Now the interval could be discrete. It can also be continuous. And then the ratio is usually continuous. But this is probably a good enough picture to try to make the distinction in the different levels as compared to quantitative and qualitative, and as how they relate to discrete and continuous. Okay? All right, so it's a little bit past 8:30, so I guess now would be another good time for a break. Remember, next time we're only going to have one break in the middle. So, you guys want to take a break or? What? What? 9:30. Yeah. So let's take a little break, 2-minute break, and then we'll get back to it, just so I can get myself organized.